Okay. All right. Hi. So, oh no. Okay, that's good because that file was actually secret. A few things today. We are going to do something called Valgrind, which you'll be practicing in the lab this week as well. This is the wrong folder, but that's okay. And then what we'll do is basically use, what we've learned in order to make something like strings in Python. If there is time, I'll also, as promised last week, show you some tricks with plus and pointers and stuff like that. So today, I think this is week 5, right? So that means just call it week 5. Okay. Oh, I actually had it here. Doesn't matter. Okay. So, okay, all right. So the first thing that I want to show is Valgrind. So going to be lecture 1. So spelled like this. It's pronounced Valgrind because it's named after, I keep forgetting, it's like something in Norse mythology. It's like something to do with Norse mythology anyhow. It's also a pun, so it's like grinding through values or something like this. But like Valgrind, like this is how you're supposed to pronounce it. So it's a tool for detecting memory errors and leaks. And it's a little bit annoying to install on anything that's not Linux. So it works just fine on ECF. It should work okay if you're working on WSL on Windows. Anything else, probably not so much. So we will have it installed on Gradescope so that you can use it by basically submitting on Gradescope and getting the output, but we have not done it this year yet. So this is how it works. So let's say that I have something like a memory leak. So I'll allocate an array and I'll forget to free it. So basically, in order to run it, you run it in the terminal. What the workflow that I suggest is first running the program. So I'm running it here. Forgot. Okay, so basically what the run button does, okay, it's run now. So what the run button does is it runs GCC in the background, right? So if I look at what the files are that are available now, there is now the program lec1 that's been created by the compiler. So just kind of to show you that it wasn't there before, delete it, move to trash. And then if I run it again, I'll do like a print hello as well, just to show that it does something. And I'll include stdlib.h so that malloc is not anymore giving me a warning, even though it was working fine before as well. If I save it, the thing is going to go away eventually. Oh, I didn't print anyways. So the return 0 is also optional. It will return 0 by default. Okay. So what you should have noticed is that the LEC1 reappeared. So that's the program. I can also run it in the terminal like so. And that also printed hi. So that was me running the program LEC1. On Mac, it'll look the same. If you're running on Windows, it will be named lec1.exe. Right. So the point of the exercise was to eventually run Valgrind. So I can run Valgrind like so. And what Valgrind does is it basically is running the program, so running LEC1, but keeping track of stuff, including what was allocated with malloc and what was freed. And what you can see here is it says that there is a memory leak of 40,000 bytes, which makes sense because size of int is 4 and I allocated 10,000 ints. Make sense? So now if I want to fix it, I'll say free array. So I'll rerun it again. This is not running Valgrind. It's still just going to print hi over here. But if I run Valgrind again, now it's going to say that it is all fine. Make sense? So you can also create the same thing in the terminal. So I think I made you do it in the lab the once. I don't recommend compiling in the terminal. This is not the way we do things by default. So if you do it though, so if you say lec1c, so if you remember, this is how you specify the name of the program. You can name it whatever you want, like anxi.exe is fine, even in Linux, that's fine. You do have to say -g as well for Valgrind to then work on anxi.exe. So if you run, so one thing that you notice is that anxi.exe has appeared here. You run it like this, still going to print hi. And then if you run Valgrind on this, that is going to say no leaks detected. But that's just because I freed it. So like if I comment it out and I saved, I compile again, run again. Now there's going to be a memory leak. Make sense? And again, I did not explicitly say today, even though I said multiple times in the last 2 weeks, a memory leak is when you malloc, but you fail to free. Okay. Questions so far about mechanics of this? Okay, so memory leaks ordinarily in the kinds of programs that we run are just not a big deal. Technically, it's a memory leak. In practice, the operating system is going to take care of it for you. A bigger problem is stuff like this. So if I say something like printf, and then they say like array at 10,000. So that is undefined behavior, right? The reason it's undefined behavior is that there is no array at 10,000. There is array at 9999, but that's not an element that exists. Sometimes it would crash. Worse, sometimes it would print something that could be anything. So I'll run it and see what happens this time. And what happened this time is, in a way, the worst thing that could happen, which is that it actually ran and it actually output 0. So it looks like everything is fine. Nothing is fine there, right? It could have crashed. So so Valgrind is unfortunately not 100% reliable. We'll try it. It usually catches it, but we'll see. it did catch it. So as you see, there is an error. So the error is that over here, it tells you on line 11 in main, you accessed an element that you were not supposed to access. Okay, and it says this is 0 bytes after a block of size 40,000. So that's really kind of the usage of this kind of thing. Is it could be that it runs and it's all fine, except it's not actually fine, and Valgrind is going to help you find that. For example, like if you submit something like this and it kind of works on your computer, it's not guaranteed to work with the autograder because what this is it's actually illegal. Okay, so here is another example of undefined behavior. So I got rid of that, and I'll do a free just so that don't get caught in this. So if I say like if array at 0, I'll say print something like this, right? So why is this bad? Yeah. Oh, you were just raising your, yeah, yes.
Say what array of 0.
Exactly. I never initialized array at 0. It could be anything. So I'm allowed to access array at 0. That's a valid address, but I never initialized array at 0. So it could be anything. So just like when you go on Acorn and you check your praxis grade, you can run it and see what happens. Apparently not. So in this instance, it did not print it. If you run Valgrind, again, this is like a live demo. It could work. It doesn't always work. So here it says conditional jump or move depends on an initialized value, so which is exactly right. So in line 12 over here, what it means is that array at 0 was not initialized. Array at 0 not initialized means you didn't assign anything in particular to it, so it could be anything. In this case, it appears to have happened not to have been greater than 0. It's probably 0. Okay. All right. Questions about this? All right. So again, you can try to make it work on Mac. I do not recommend it. It's very annoying to do. It works completely on ECF. It will be set up on Gradescope. It's not ideal to run it on Gradescope because it takes like 10 seconds for you to submit and get the output from Gradescope, so it's just annoying. On ECF, it does work. Okay. And when project 1 is posted, which will be in a few days, one of the requirements will be that submission for project 1 that you submit does not produce errors when you run it on Valgrind. So Gradescope is going to tell you when you submit whether it did or didn't, but it's not ideal to debug it on Valgrind. On Gradescope, rather than kind of figuring out a way to run Valgrind on kind of in a way that gives you feedback immediately. All right. Okay. Questions about this? All right. So the next thing that I want to do is show you a situation where it's so bad that it will crash when I run it in VS Code. Again, I need to actually try various things until I actually manage to crash it, but it's probably going to be fine. So I'll allocate 100 and I'll try like something crazy like this. And if I try something if you remember, it did not crash, even though it could before, but here I made the index so large and the memory block small so that probably VS Code would detect it. So if VS Code does detect it, then if you run it in VS Code, it'll just tell you when you run it in the same way that Paizo just crashed and told you I'm crashing on this line, it'll tell you what's going on here. So if you then go to here, so this is the run and debug tab on in VS Code. You can actually see what the values of the variables are. So for example, you could say, oh, like maybe it crashed because I forgot to malloc it all. That's not the case here. And you can see that it's not the case because array seems like it's like some kind of address that's probably valid. So that's fine. Over here, there's no variables defined, but if you had defined some kind of variable, so I'll stop debugging here. So if I do define a variable over here, whatever a is equal to 42 or something, and then I run it again, and hopefully it does crash again, then you'll see the value of a that was the value of a before the crash had occurred. So again, this is over here in the run and debug tab. Makes sense. So that's convenient. Again, unlike with Python, where everything is kind of easy and like there is no uncertainty about what's going to happen, here sometimes you put in an error that's kind of subtle and it's just going to run, and Valgrind might or might not detect it, but the debugger itself might just not, as you saw in the example before. Make sense? All right. So that is this. And in the lab, you are supposed to demonstrate doing all of that. Okay, so let's, by the way, yeah, so this would be the same error, just like more drastic, where we are accessing an address that we're not supposed to access. All right. So the next thing that I want to do is header files. So we kind of already were using header files. So, and what we said is that the hash include is kind of like import in Python, which is what it is. I just want to tell you in more detail about how it works. So by convention, it doesn't have to be, but by convention, header files are .h. H. So ordinarily, the way it works is you can do anything in the header file. So you can say something like, I don't know, and so this is just a function. So whatever, like F42, return 42. And then what happens if you include it? You say include funcs.h. So if it's a custom header file, it would be in double quotes rather than in angle quotes. Angle quotes means go to where the built-in header files are. This means go to the current folder. And what this does is essentially copy and paste, not essentially, like literally copy and paste. So it's as if you just took this stuff and you copied and pasted it into lec1.c. Okay. So that means that over here, you got to say F42. Let's say I want to print it. And you got 42. So it's as if, as if you just copy and pasted the definition of that function. Okay. So the more usual way that you use header functions is not actually that. So what you usually want is for this to just have the, I'll post the notes. I'm sorry, I'm behind on that. So what you usually want is you just want to post the signature. And then you want the implementation elsewhere. So I'll save this as funcs.c. And then I'll define the function like this. So this would be return 42. So if I do it like this now, that is not going to work. And the reason it's not going to work is that what I did is I included this guy, which I'm allowed to do. So you're allowed to include the signature here, but that's essentially a promise. Like there is an F42 somewhere that you're going to be able to use. I did not actually say in lec1.c anything about where F42 is. So the problem, where's my problem? That's from before. Let me just run it again so that I get the prompt. Show errors. Okay, it refuses to show the errors here, which is unfortunate. But here, what it says is undefined reference to F42. So that is because F42 is never defined. All that's done is this signature is provided. The actual function is not defined. So I'm going to show you how not to do it first. And then I'll show you how I'm going to make you do it next week. So what you can do is you can say gcc lec1c funcs.c. So here I'm creating a program with the name anxi.exe. I don't need the -g because I'm not planning to run Valgrind on it. You'll notice that this compiled, and if I run anxi.exe, that is fine, that'll run. Okay, so the structure here is funcs.c tells lec1.c is fine because F42, there is a signature there. So that's like a promise that it's somewhere. And then when I actually compile it, I say compile both of those guys together. So that makes it so that it works. Unfortunately, if you do it this way, which many students actually tend to do because that's like the path of least resistance, you can then not debug it with breakpoints and stuff like that. So what you want to do is you want to be able to use the run button, which you currently cannot. So to run it with the run button, what you got to do, and that's just life, it's a little bit annoying to do, is you say terminal, say configure tasks. You select probably the first one. It's supposed to be C++. That might be different on different systems. And over here is what VS Code is supposed to be doing when you run it. So you're not supposed to be able to read like all of this stuff, but here's basically what it's saying. It's saying run GCC. So here what you will see is your version of GCC. For some people, this would be Clang, which is a different compiler. Then you have the -G, which is something that we've done with you as well. And then you have -O and then the name of the file. Ordinarily, the name of the file would be the same as the lec1.c, except it's going to be like just lec1 without the C. This is what this means, like file base name, no extension. So this would convert to lec1 if the name of the file is lec1.c. This would convert to lec1.c. This is like the file. So what you do, and that is the way, I'm sorry, is instead of the file, you say lec1.c, and you say, oh, also funcs.c. Like so. You save it. And now you run it. And now it's fine, and you can have breakpoints, everything's great. All right. So it is annoying. At the same time, this is the kind of thing that Claude Code still cannot do, whereas you might be able to. So, okay. All right. So that's like this. So one more thing about the header files is what's called header guards. So this is a way to make it so that an H file is not included twice. So I'll just do it kind of, I'll tell you why it is that way, but I'm not really going to test you on it. So it works like this. So basically what's happening here is this is a way to just say I'm defining the symbol funcs_h. This is just the name. It could be anything. And here I'm checking whether it's defined or not. So this entire block is going to be just nothing if funcs_h is already defined. And it's going to be this thing if funcs_h hasn't been defined before. Does that make sense? So that allows me to include this as many times as I want. In this particular situation, it doesn't matter. I could do it anyways. Later on, it is going to matter. But now what I can do is I can just say, you know, include funcs.h over here, and I don't care that I've already included it. Again, in this particular case, I could have done it anyway. In some situations, if you try, for example, to define a function twice, the second time you try to define it, that's going to be an error. So that's a way to avoid that. What I suggest is just any time that you write a header file that you just include a header guard, because why not? Make sense? Why include it here? Well, like it's good practice because if I happen to have gotten this wrong somehow, then I'll get an error, right? So here, if I define F42 in a way that doesn't conform to the signature, that's going to produce an error. So including, in this case, function.h serves the function of just making sure that they don't make a typo when actually defining F42. Okay. In other cases, it's more crucial. Okay, makes sense. So that was mostly showing you the mechanics of this. If you look at past midterms, there is certainly, define a header file, this and that definitely exists. Mostly, obviously, what I'm showing you now is just making sure that you can actually do it in the lab. So like you got to see how it's done first, and then you can do it. All right. Okay. So that's like that. I'm not going to take questions about this just because like you just got to try it and make sure it works more than anything else. But if you do have questions, okay. All right. So we have not very much time left, but I want to at least start doing, okay, well, some people decided for me. So I want to at least start doing something substantive here. So what I'm going to do is I want to implement something like Python strings. And what I mean by that, CPP. And what I mean by that is something like that. So I want to be able to say something like my string S1, and then I want to be able to say like create string. So I'm like making up syntax here, and then I'll make it so that they can actually do it, right? So I want to be able to say like create string, whatever, like initially it's high. So like, and then I want to be able to say append strings S1, S2, and I want to say like S3 is append string S1, S2, and they want like S3 to be equal to S1 plus S2 essentially. So I just want to be able to do stuff like that. Right? So how do I make it work? So in order to have a type like this, it's got to be that I have to have a struct. And then I want to be able to do something like this. This, by the way, has to be my string. So, okay, let's start doing it at least. So I have to have the contents of the string stored somehow. So that's probably going to be in a character array. So the usual name for this is buffer. So buffer just means like basically a block of memory. That's like the usual name that people use for that. I probably want to know how much, I'll probably want to know the length of the string. I probably also want to know what the size of the buffer is. So it might be that the length of the string and the size of the buffer are not the same thing. So like maybe something like this. Right. So create string we already had done, or like something like that. So this would take the address of a my string star. So that means my string star star. And this is the kind of thing that we've already done. So this would be my string star malloc size of my string. So I also wanted to actually be able to initialize it to something. So one way to do it is to just make the buffer be the same size as the initial string and then copy it to it. So size of car is 1, so I'm not going to multiply by 1. The +1 is to store the null. So that means that the buffer size is this much. And now I can copy to the buffer from the initial string. And I can say is something like this. Make sense? So this is, I did it kind of quickly because we did exactly this kind of thing before as well, right? So what I want to do now is basically I named this use strings. So I might like to not just copy and paste it into every file that uses strings. Instead, I want to put it in an H and a C file so that I can use it from multiple programs. So that's what I'm going to do. So the convention and the thing that's the safest to do without getting into the weeds is only define functions in .c files. Everything else goes into .h. So the everything else is this. So this will go into mystring.h. And like, so this is mystring.h. So like just do it like that. There are situations where you can get away with some other kind of configuration. Just don't think about it. Just all the structs go in the H file. The function signatures, but not the functions themselves, go into the H file. The function definition goes into the C file. So I'll make a mystring.c. And I'll move the function definition to mystring.c. So here you'll notice that my string is underlined and malloc is underlined. My string being underlined is critical because this file, unless you say include mystring.h, will not know what my string is. So the malloc on my system is not critical, but might as well include stdlib. That's fine. Right? So now what I'm going to do is I'm going to include mystring.h over here. So this is still not implemented. but create string is implemented, so that should be able to run. Except it won't, because if I run it right now, what's going to happen is I'm going to print 42 again, because in my tasks.json, what I said is compile lec1.c. So I need to go to tasks.json again, because I'm still in the same folder. So go to configure tasks. And here I'm going to say use strings .c. And I'm going to say mystr.c. So what's given to GCC is just the C files and all the C files. The H files do not go here. They do not need to go here because they include just copy paste them anyway. So now that that's like this, that is going to be fine. And it ran and did not print 42 because now I've actually done the thing that I was supposed to do. So you could also say GCC use string C mystr.c, something like this. That just warnings because it neglected to include inside string.h. This works. People, again, are just like very tempted to just do this because at first configuring tasks.json is annoying, but it's not that annoying. It took me 5 seconds, so just do it. All right. And the beautiful thing is once you've defined mystring.c, you can use it in any program as long as you specify it in tasks.json. Okay, I will see you Wednesday. See ya.